Okay, so as you can see here, we have a compound on the paper. It's isobutylbenzene, and today we're going to be talking about how to take this compound and use it to synthesize ibuprofen. You've probably heard of ibuprofen, probably taken it. Ibuprofen is one of the biggest NSAIDs on the market right now, NSAID standing for non-steroidal, anti-inflammatory drug. And so the cool thing about this transition is that isobutylbenzene is actually a respiratory irritant, and it's also flammable. But obviously, when it's converted here, it converts into something that's used as an NSAID. So a little bit of information for you there. So in order to do this, the first reaction it's going to undergo is a Friedel-Crafts acylation reaction. Okay, so just to give a little bit of background into the Friedel-Crafts acylation reaction, let's just draw a mechanism here that kind of shows what's going on. So we have a benzene ring, okay? All right, so the way that this reaction is going to work is you're actually going to have this Cl grab onto that aluminum right there, and then breaking this bond. So that is the first step. This will then become a carbocation. So let's go ahead and show that. So we still have the benzene. And then now we have a carbocation. And then we have, of course, the Cl3Al bonded to the Cl. And that Al now has a negative charge. Okay, awesome. So basically what's going to happen here, what's going to happen next is this benzene double bond here is going to go ahead and grab that carbocation. And so it's going to look something like this. And then, of course, you have that R group on the side, whatever R is. Okay. Now, there's a hydrogen right here. And this hydrogen is going to be grabbed by the electrons here at the AlCl4. It's going to be grabbed by that molecule. And then, as a result, the electrons from the H are going to go back into the benzene ring. So you're going to be left with sorry about that, it seems to go off the page. Let me draw it down here. Awesome. So now that you kind of get an idea what the Friedel-Crafts acylation reaction is, let's go ahead and go back to our isobutylbenzene. So we're going to do something very similar here. So we're going to have this reagent, double bonded to O. Sorry if that O is kind of small. Let me actually, hold on. Let me do this. That way it's clearer. So we have the C double bonded to the O, and then bonded to a Cl, and bonded to a methyl group, so CH3. And then we're going to, of course, have the aluminum Cl3. So I've already explained how this reaction occurs, so I'm not going to explain it again. But if you need to go back and rewind, you absolutely can. But basically, you're going to be left with the following. Sorry about the dog barking. Okay, so you're going to be left with the following. And this is going to be a compound known as isobutyl acetophenone. Okay, awesome. And then what we're going to have to do here is we're going to do a nucleophilic addition reaction in the form of HCN. So hydrogen cyanide here. So let's just go down here. We have hydrogen cyanide. Awesome. So as with any nucleophilic reaction, what you're going to have here is the CN is going to, hold on, CH3, CH. Let me go ahead and write it down for you guys. CH2. All right. So what's going to happen here is you're going to have, obviously, the CN attached where the O once was in positioning here, but the O actually becomes the OH that's down here. All right. And so this is called cyanohydrin derivative. So it's called the cyanohydrin derivative, and I'll just leave that as abbreviated deriv. And so then the last step here is a hydrolysis reaction. So you're going to take HI and P and H2O, and this is a hydrolysis reaction. Awesome. So basically what's happening here, so the I'm not going to draw the mechanism, but basically all that needs to be known here is that the cyanide is undergoing cyanide, when it undergoes hydrolysis, produces a carboxylic acid group, and the and also in this reaction the OH is going to be replaced with an H. So what that's going to give you is, of course, our wanted end result here, which is ibuprofen. So one thing to note while I'm writing it down here is that ibuprofen has a chiral carbon, which I will show you momentarily. Oh, whoops, appears as though I messed up. Let me just draw it down here. That way it's a little bit more visible. There we go. So as you can see here, this is that carboxylic acid I was mentioning earlier, and then this is where the OH is reduced. So that is ibuprofen there. And so basically, one thing of note, like I said, is this is actually a chiral carbon. And so there are two enantiomers of ibuprofen. One is the S enantiomer, and the other is the R enantiomer. And so the cool thing to note about these two guys is that the R enantiomer is actually completely inactive in the body and is converted to the S enantiomer by your body. And then, of course, the S enantiomer does what I said earlier and works as a non-steroidal anti-inflammatory drug. So, yeah, with that being said, I think that's the chemical reaction, synthesis reaction for ibuprofen. So, thank you.